Swayam Prabha. Digital India. Educated India.
Hello everyone. We have been discussing the idea of resistance in ballistic and diffusive cases, and since last class we started doing actual calculation of resistance and comparing that to the conventional idea of resistance that we generally have from our classical theory of transport. And this is what we understand from the classical theory of transport, that the resistance is given as is generally proportional to length. Resistance is considered to be proportional to length in 1D case. In 2D case, resistance is directly proportional to length, inversely proportional to width. And in 3D case, resistance is directly proportional to length and inversely proportional to the area. And the constant of proportionality is known as the resistivity, denoted by rho, which is essentially the inverse of conductivity. That's our classical understanding of resistance, and conductivity is given as N times Q times mu, where mu is the mobility of the carriers, and this N will be the number of carriers per unit length in 1D conductor. It will be the number of carriers per unit area in 2D conductor, and it will be number of carriers per unit volume in 3D conductor. In contrast to this, our discussion of conductivity starts with this expression, which we obtained from the general theory of transport and or the general model of transport. And in this expression we have this constant which is known as the quantum of conductance, and in integral we have TE integrated over this function, which is also known as the Fermi window function. So, the Fermi window function is minus del F by del E, and with this expression we started doing calculation of resistance for ballistic case in our previous discussion, and there we saw that at 0 Kelvin, at extremely low temperatures, this function, the Fermi window function, boils down to a delta function, and which essentially simplifies this integral greatly, and the conductance that we obtain is essentially this. So, at low temperatures, when T approaches 0 Kelvin, in that case this is the ballistic resistance of the device. So, in this case what just needs to be done is we just need to calculate this MEF parameter, which is the number of modes at energy EF at 0 Kelvin. And we also saw that this term, MEF term, this can be related to the sheet charge density, number of electrons per unit area in a 2D conductor, and the relationship looks like this. So, the MEF value can be written as W times M2DEF, where M2DEF actually turns out to be square root of 2ns by pi. This we saw from our previous discussions, and finally this is the conductance that we obtain, and by putting an appropriate value of MEF we obtain the value of the conductance. So, all this was true for low temperatures when T approaches 0, which means Fermi function is approximately a unit function and Fermi window is a delta function. In those cases, the calculations are easy. Then we started doing calculation for above 0 temperature cases, at room temperature cases. So at those temperature values, we realized that this Fermi window function can no longer be approximated by a delta function, and in this case this integral needs to be evaluated properly, and now this integral also has a derivative with respect to E, which can be converted to derivative with respect to EF. Okay. And after doing calculations at room temperature for the conductance, we realize that we come across a special type of integral functions. Those one we defined as Fermi-Dirac integral function. Those are the Fermi-Dirac integral function. So generally in these calculations we need to know about the Fermi-Dirac integral functions, and that's what we will quickly go through. A Fermi-Dirac integral function looks like this. It has a Fermi-Dirac integral function of order j is defined as 1 divided by gamma function of j plus 1 integral over eta power j d eta divided by 1 plus exponential eta minus eta f. This is how a Fermi-Dirac integral function of order j is defined. The parameter this Fermi-Dirac integral function has the variable eta f in its argument. Please remember this. On the right hand side we have both eta and eta f, but in the argument of the Fermi-Dirac integral function eta f is there. Okay. The order j depends on the exponent of eta in the numerator on the right hand side of this function. So if we closely look, this j, the order of the Fermi-Dirac integral function, it depends on the exponent of the parameter eta, and the argument of the function is eta f. This Fermi-Dirac integral has this gamma function as well in its expression, and most of us would be aware that a gamma function, if j is an integer, this is equal to factorial j, or if n is an integer, gamma function of n plus 1 is essentially factorial n, or more popularly it is written as gamma function of n is factorial n minus 1. Okay. There is another property of gamma functions, which is gamma function of n plus 1 is n times gamma function of n, and gamma function of half is essentially root pi. Okay. So this is essentially the summary of the gamma function, and with this gamma function we can define the Fermi-Dirac integral function, in which there is an integral which looks like this, which is essentially integral over parameter eta of the term eta to the power j divided by 1 plus exponential eta minus eta f, and along with this we have a normalization factor of gamma j plus 1. So this is what we have, this is what we just discussed for the gamma functions, and there is for non-degenerate semiconductors. So there are generally, depending on the doping of semiconductors, are divided in two parts, in two types. One is the degenerate semiconductors and second is non-degenerate semiconductors. Generally in moderate doping situation, when the doping is not too much, which means that the dopant atoms are far away from each other, they are not interacting with each other, they are not talking to each other, the potential due to one dopant atom is not felt by the another dopant atom. In that case, the doping is known as the, or the semiconductor in that doping is known as the non-degenerate semiconductor. And generally the Fermi function is way below than the bottom of the conduction band. So in that case, in non-degenerate cases, EF is less than EC generally, or at least EF should be sufficiently below EC, which in other words is written as EF minus EC can be written as KT is less than 0, it is much smaller than 0. Okay, and this thing we if you remember, this is what this parameter eta f is. So in non-degenerate semiconductors, generally eta f is quite smaller, it is it is a negative number and this is less than 0, and in those cases this Fermi-Dirac integral of order j, in this case, in non-degenerate case, this, please remember that this is the case of non-degenerate semiconductors, and in these cases eta f parameter is less than 0, is way less than 0. So in these cases this Fermi-Dirac integral can be approximated by exponential of eta f. So this is an important approximation, which is true in most of the cases, because in most of the cases our semiconductor is non-degenerate. So this can be approximated by, so these are few mathematical, I would say bits that if we keep in mind, these calculations, those the calculations that looked so difficult, those calculations will become easier. Okay. So just keep all these things in mind, otherwise this evaluation of the integral in conductance becomes extremely difficult. Okay. In addition to all these properties, we also and this also I also mentioned last time, that if we take a derivative of Fermi-Dirac integral with respect to parameter eta f, the order of the Fermi-Dirac integral decreases by 1. Okay, just that. And this is useful because in addition to integral, we also have a derivative in our conductance expression. So this thing and this along with these, they will greatly simplify all our calculations. So just keep these things in mind. You don't need to remember these things, because not to complicate things in too much of details, but these mathematical bits are discussed just so that the calculations do not look too difficult to you. If we remember these few points, the calculations involving the Fermi-Dirac integrals are not extremely difficult, are not that difficult. We can manage them. Okay, especially in the non-degenerate semiconductor cases. Okay, so with this we continue our calculation that we were doing last time. In last class, we were discussing the resistance of a ballistic conductor, a wide ballistic conductor at room temperatures, I would say, or higher than 0 temperature. So in this case, we were doing the calculations, and we saw and I also mentioned this, that in this case this Fermi window can no longer be approximated by this delta function, and so that is why we again need to start from this expression of the conductance. Please remember that the expression of conductance to begin with in any case is this 2q square by h TE minus del F by del E dE. And if we explicitly write down the Fermi function in this derivative, in this Fermi window, this is how it looks like. Fermi function is 1 divided by 1 plus exponential E minus EF by kT. In these expressions, just to remind you, this Kb TL is written, where Kb is the Boltzmann constant and TL is the lattice temperature. We are in short writing KT. Okay, so with this we make this replacement minus del by del E is replaced by del by del EF, which allows us to bring this del by del EF outside the integral. So inside the integral, what is left is this constant is outside, and inside the integral we are left with terms involving the this m2d function, this number of modes in a 2D conductor, and this Fermi function, and this is essentially all these terms. Apart from these terms, these were constants, and these constants come out of the integral. So finally, this can be written down in terms of Fermi Dirac integral, and as you can see here, eta to the power half will be there. So if we make this replacement, eta is equal to E minus EC by k times t, and eta f is EF minus EC divided by kT. And if we do this replacement, apart from this constant term, what is there is we are left with a derivative with respect to eta f and an integral with respect to square root of eta divided by 1 plus exponential eta minus eta f d eta. This we saw in our last class as well, and today with the background, with a bit of background of Fermi Dirac integrals, this thing is now more clear. I hope this is more clear now. So as we can clearly see, this is the Fermi Dirac integral of order half, and with some constant in it, and if we make the replacement, if we replace this integral by the Fermi Dirac integral of order half, then what is left is apart from this constant term, now in addition to this constant we also have square root of pi by 2, we are left with d by del eta f Fermi Dirac integral of order half. Okay, and as we saw that if we take a derivative of the Fermi Dirac integral of order j with respect to eta f, then it becomes the Fermi Dirac integral of order j minus 1. So the order is reduced by 1. So ultimately this becomes Fermi Dirac integral of order minus half. Okay, so finally the conductance of a ballistic conductor, a wide ballistic conductor at normal temperatures above 0 Kelvin temperatures is given by this expression, and in this expression please keep in mind that apart from this constant term 2q square by h, everything else is written as average some sort of average of w times m2d, where this average of w times m2d is square root pi by 2 w m2d kt, m2d evaluated in kt, Fermi Dirac integral of order minus half. Okay. And as we saw from our, as I just mentioned a few minutes back, that in the case of non-degenerate semiconductors, generally the Fermi-Dirac integral function can be evaluated quite easily. It becomes just the exponential of that order. There are also few things that I would like to sort of highlight here. I mentioned that the semiconductors can be of two types, degenerate or non-degenerate semiconductors. So, when in moderate doping, in realistic doping situations, the semiconductors are non-degenerate semiconductors, and when we have extremely high doping, generally we have degenerate semiconductors, and in degenerate semiconductors the Fermi level lies quite close to the conduction band. It may even lie inside the conduction band. So, if the Fermi level is if this is the top of the valence band, this is the bottom of the conduction band, and this is the Fermi level. Fermi level is somewhere in between or slightly closer to the, or if this is the Fermi level, this kind of semiconductor is non-degenerate semiconductor, because this distance, this EC minus EF is many kTs. Okay. But if the doping is extremely high, the dopants are placed very close to each other in the semiconductor, this EF comes very close to the conduction band edge, or it may even go inside the conduction band. So, the Fermi level may lie here. So, in the degenerate semiconductor case, as you can imagine that the electrons in the conduction band will be spread in many or the electrons will be, the conduction band will be more filled in a way, and electrons will occupy many kT energy states. So, it will be NKT, many kT energy states. But in the case of non-degenerate semiconductors, the electrons in the conduction band are not too many, and so if we talk about the non-degenerate normal cases, in non-degenerate semiconductor cases, there are only electrons are only there in a small range of energy values, or around 1 or 2 kT energy range. So, just above the bottom of the conduction band, only up to 1 or 2 kT energy values, the charge carriers are there in the non-degenerate semiconductor cases. So, that is why these Fermi-Dirac integral in the case of non-degenerate semiconductor cases, that is why we can replace this eta f to be quite less than 0, or we can evaluate, or this can be this number of modes can only be evaluated for certain kT values of energy. Okay. So, this is sort of a restatement of the fact that we discussed in the last slide, that is this condition essentially. So, in this case, in non-degenerate semiconductor cases, even eta is quite close to 1, because now the energy values of electrons is quite close to EC. It is only 1 or 2 kT, within 1 or 2 kT values of EC. So, this value is also within 1 or this is around 1 to 2, mostly around 1. So, with this now this expression of conductance of a ballistic conductor at above 0 Kelvin temperatures, this is what we obtain, and we have now written it down as 2q square by h times average of W into M 2D. And the reason and this average of W into M 2D is essentially square root pi by 2 W M 2D KT. And this W M 2D KT is actually W times this value. Okay. So, what I mean to say is that this constant here in our expression, this constant is essentially W times M 2D evaluated at KT, and this is justified in the case of non-degenerate semiconductors because electrons only occupy around 1 or 2 KT, or in most of the cases around 1 KT of energy range in the conduction band. So, this accounts for most of the electrons in the non-degenerate semiconductors. So, that is why these constant terms can be written as average of W times M 2D. Okay. So, what we finally realize is that the conductance in a ballistic conductor at room temperature, let us say, can be written as 2q square by h W times M 2D, or it is written as 2q square by h average of M, where this average of M is essentially M 2D KT Fermi-Dirac minus. So, what this means is that this average of M is the average of modes in the Fermi window, okay, in the energy range of KT. That is true for the non-degenerate cases. So, and if you recall that at T equal to 0 Kelvin, the conductance was essentially 2q square by h M EF. So, what changes at room temperature is this. So, instead of M EF, now we need to use M average of M. So, this average of M is the average of modes inside the Fermi window essentially, and the Fermi window also at room temperature generally is only around 1 KT above the conduction band edge. Okay. So, that is the only difference that we see in our treatment of, or in our calculation of conductance at room temperature. We just need to replace MEF by average of M, where average of M is given by this expression, and these are the number of modes or number of conducting pathways in the Fermi window. And as we also saw in our previous case, in the case when we had this experimentally available parameter Ns, sheet carrier density of electrons, we could calculate the conductance and resistance in terms of Ns. Similarly, in this case, we can calculate, or we can have a relation between the conductance and the sheet carrier density. In this way, the sheet carrier density is defined as is pretty evident, sheet charge density is this is the density of states in a 2D conductor times the Fermi function dE, and now this needs to be evaluated for all energy values at room temperature, and this turns out to be m star kT divided by pi h bar square into Fermi-Dirac integral of order 0. Okay. Okay, and by sort of dividing these two expressions, we can have a relation between the two. So, the resistance will be just the inverse of the resistance of a ballistic conductor at room temperature will be just the inverse of the conductance. And as we saw from our classical theory of transport, that the resistance is always proportional, directly proportional to length, but in this case both at 0 Kelvin and at room temperature resistance is independent of the length, okay, in the case of 2D conductor. And similarly we can also see for 1D and 3D conductors that resistance is independent of the length of the conductor. Okay, it depends, it is inversely proportional to the width, because the conductance is directly proportional to the width. So, the resistance will be inversely proportional to the width of the conductor. Okay. And that is also understandable because the width, more the width, more will be the number of modes and less will be the resistance, or more will be the conductance. So, this is how we can do calculation for conductance and resistance in realistic situations for a ballistic conductor. Now, the next topic that we will begin with, we will quickly calculate the conductance and resistance of a diffusive conductor. The calculation is pretty similar to what we did for the ballistic conductor case. In that case, we, in addition to everything else, we would also have this transmission coefficient. So, in this expression of conductance 2q square by h integral of T e m e minus del f by del e d e, we would also have the, to include the transmission coefficient in the case of diffusive conductor, and those calculations we can now quickly do because we are now familiar with the Fermi-Dirac integrals, we are now familiar with how to sort of deal with this kind of calculations. Okay. So, that's what we will see in the next class. Thank you for your attention. See you in the next class.